Hi, I'm Bingyan from Peking University. I'm going to talk about our recent work, PMC, a privacy-preserving deep learning model customization framework for edge computing. This is a joint work with Microsoft Research. Recently, it becomes increasingly attractive to deploy the CNN models to edge devices to protect user privacy and reduce inference latency. Traditional pipeline for edge AI includes three steps. First, we train the model with the cloud data collected from various sources. Then we compress the cloud-trained model to match the device constraints. Finally, we deploy the compressed model to each edge device. However, in our scenario, the training data in the cloud is statistically different from the deployment environment. Thus, directly deploying the cloud-trained model to different edge devices will lead to distribution shift, resulting in bad performance. Domain adaptation techniques are designed to address this type of issue, which typically requires joint training on data from the source domain and the target domain. In our case, it means that the cloud must collect raw data from the edge device to train a specialized model, which is undesignable due to privacy concerns. In this work, we proposed PMC, a framework to achieve the privacy-preserving model customization for edge deployment. The key idea is to employ the privacy-preserving representation to replace the raw data for later processing. Specifically, it includes three key steps. First, we extract the privacy-insensitive statistics. Then we simulate a dataset by data reweighting. Finally, we utilize the reweighted data to conduct a model compression and a retraining process. During the pipeline, we face three technical challenges. The first challenge is how to characterize the data distribution on the edge device with a small set of statistics. We address this challenge based on a main observation. The activation values of a dataset's intermediate channels conveys the data distribution information, which can be roughly modeled with Gaussian distributions. Inspired by this, we extract the channel-wide statistics and upload them to the cloud. The second challenge is how can we guarantee the privacy of uploaded statistics? That is to say, how to make sure no private user information can be inferred from the statistics. To solve this, we adopt differential privacy to provide rigorous privacy guarantee. The third challenge is how can we generate accurate models for different edge devices based on these statistics. Here we design a data reweighting scheme based on the uploaded statistics and use the reweighted data to further customize the pre-trained model. Next, we introduce our experimental evaluation. We use three public datasets to simulate different scenarios. As shown in the table, PMC outperforms other compression baselines, especially when the pruning ratio is large. Besides, PMC can exceed the state-of-the-art method EdgeAl and achieve comparable performance to AFA, which is a method without privacy guarantee. We further explore the channel selection strategies in PMC and find the best choice for each component. In summary, the best practice of channel selection in PMC is to select 50 to 100 channels from an intermediate convolutional layer based on the magnitude of mean activation values. We also tested on other models and datasets, and the conclusions are the same. Finally, we conduct a real-world user study, where we test if the extracted statistics can describe the data distribution of users. The figure shows that PMC can distinguish users coming from different environments. To summarize, our work makes three contributions. First, we introduce a new idea of privacy-preserving model customization. Second, we propose the PMC framework to achieve our goal. Finally, we conduct extensive experiments, which validates the effectiveness of PMC. Thanks for attention.